那个就是有技巧性吗？还是一般人都能识别？还有人就是数学？
没有，那个没有技巧性，主要是让你看故事，顺便下雨。
Okay, so let me remind you of where we are. We're gonna the exam will be a week from today. No.
2 weeks.
2 weeks from today, which is March 7th? No, yeah, 2 weeks from today, March 7th. There'll be a review of some sort on March 5th. I will not be here, but Stetson will, and he'll go through pretty much an overview of what we've done, and the test will cover up to. So we're going to pretty much finish what we need to today, but it'll cover up to page 116. From chapter 3, we won't do spanning trees at this point, and we won't do any of the algorithms. Okay, we'll come back to that later on.
You said 116?
Up to page 116.
Yeah.
Am I going to do a what? I thought what I would do is either Tuesday or Thursday of next week, I will have like a practice exam. Okay, and I'll give it to you, and then Stetson can go over most of that on March 5th. Okay, questions? Okay, and the homework is not due today. When is it due?
Next Tuesday.
Next Tuesday. Okay, just checking. Okay, so several people have asked me about this, and I want to be very precise on how. So graph theory proofs are much different than a lot of the proofs that you learned in Math 3000. Okay, Math 3000, you all took Math 3000 at some point, kind of, maybe. So these proofs are sometimes considerably different. But I want to go through the details of how I would write up one of these problems. I'm not going to do one that you are supposed to do, but I'd like to go back to page 89. So we spent a lot of time, and I will say that I did a lot of hand waving last week on problems 7, 8, and 9. So now I want to go through all of the detail on how I would write that up. Okay, so 7, 8, 9, we take the average, and we'll say, should I do number 8? I mean, they're all essentially the same, but a little different. And number 8. Okay, so let D1, D2, D3, and up to Dn be a graphic sequence. Show that the sequence D1 plus 1, D1 plus 1, D1 plus 1, D2 plus 1, D2 plus 1, down to Dn plus 1, Dn plus 1. Okay, so one more time. This is what I have. I know that D1, D2, Dn is a graphic sequence, and I want to show that D1 plus 1, D1 plus 1, D2 plus 1, D2 plus 1, D3 plus 1, you get the idea, down to Dn plus 1, Dn plus 1 is graphic. Okay, so here's all the detail that really will help the reader to understand. And remember, I'm not necessarily the reader. You may have other people who are reading this, like my grader. Okay, so what does it mean for D1 through Dn to be graphic? That's a question. That's a question that I'm looking for some help with. I know the answer, but.
It's possible to.
Yeah. So be exact. What does it mean for D1, D2, Dn to be graphic? Okay, so I know this, maybe it's just too obvious, but there is a graph G with degree sequence D1, D2, D3, Dn. Okay, so there is such a graph. So let's choose such a graph G. So this graph that I have G has exactly degree sequence D1, D2, D3, Dn. Now let H be, okay, so let me stop for a second. So G has vertex set of G is equal to, the vertex set is equal to x1, x2, up to xn, such that the degree of xi is equal to di. That's what it means for the graphic sequence to be realizable. Okay, that's what it means when it says that it is a graphic sequence, means that there is a graph that attains that sequence. Okay? So I've chosen G, and now consider another copy of G. Consider a second copy of this graph called, what do you want to call it? Let's call it H. Called H. And the vertex set of H, let's say the vertex set of H is y1, y2, yn, such that the degree of yi is equal to di. Okay, so now these are the words, and here's sort of what I'm looking at it myself. So I have here's G, and this is for my own benefit, right? Here's G and here's H, and here are the vertices of G, and here are the vertices of H. And at this moment, what can you tell me about the degree of the vertices in G? What can you tell me about? This is x1. What can you tell me about the degree of the x1?
D1.
And the degree of x2? D2, and the degree of xn is dn.
I have a question. Over here where you have the degree of xi equals di and the degree of yi equals di, is it okay that they both have the same?
Of course. Right? I mean, think about it. At this point. I mean, you can write them on different sets of paper. Okay.
Still call them di.
You can call this is graph G. This is the graph G, and degrees. I mean, di is a number, 7. So to say that vertex 6 has degree 7 or whatever, to say that this vertex has degree 1, it doesn't matter what this graph looks like. Okay, and these don't have to be the same graph. Okay, one more time, this is just a graph, G is just a graph that realizes this sequence. There are, there are many graphs that realize a particular degree sequence, right? We'll come back to that in a second. Okay, so here's H, and the degrees of H are the same. The vertices are y1, y2, yn, and the degree of y1 is d1, the degree of y2 is d2, the degree of yn is dn. Okay? They could be the same, they could be different. Okay? And again, we'll go through that, show that there are graphs with the same degree sequence that are different. Okay, so let's look at G. this big graph. Now, so this is a graph, and this is a graph, and now imagine I'm going to construct a new graph called, let's see, I've run out of letters, GH, let's call this J. So J is made up of 2n vertices. What's the degree sequence of the vertices in J at this point? Careful. So the degree sequence. So I have a vertex of degree.
D1, D1.
Okay, so the degree sequence of J at this point is D1, D1,
D2,
D2, D2, D3, D3, DN, DN. I haven't done anything, so is everybody with me at this point? Okay. But I need, come back here, I need D1 plus 1, D1 plus 1. Right now, I have D1, D1, D2, D2, D3, D3. I need D1 plus 1, D1 plus 1. What should I do? What is this? What is this? Tell me what you want to do.
Collect D1.
Yeah, I want to put an edge in between. This is what do we call these are the x's. This is x1 and this is y1. I want to put an edge between x1 and y1. Okay, now in this graph, and this graph, what's the degree of x1? And what's the degree of y1? Okay, so then those are the first two degrees that I need. Okay? Now what? Okay, so this is the picture. The degrees of this graph, let's see, we call this graph J. So the degrees of this graph look to be D1 plus 1, D1 plus 1, D2 plus 1, D2 plus 1, D3 plus 1, D3 plus 1, Dn plus 1, Dn plus 1. That's good because that's exactly what do we want. Okay, so now I got to tell you what J is. The vertex set of J is equal to, let's see, the union x1 through xn, union y1 through yn. That's my vertex set. And the edges of this graph J are precisely the edges of G, union the edges of H, union xi, yi for I equals 110. J has the desired degree sequence. Nope, no exclamation. Period. And now you're done. Okay, you showed that G, the degree sequence D1 through Dn is realizable. You realized it. In fact, you realized it twice. And now you showed, using those two realizations, that in fact the degree sequence, as they ask for, D1 plus 1, D1 plus 1, D2 plus 1, D2 plus 1, and so forth, is realizable. And you gave me a graph, you showed me a graph that has exactly that degree sequence. Is that clear? So this is the detail that I would like to see when you're write-ups.
So on the edge set line, so you're saying that the
This set, okay?
the edges of J equal the union of the edges of G and the edges of H, and then what's that
Union
with the vertex?
xi, no, this is an edge. This is EI is equal to the edge xi, yi. X1, Y1. This is E1. This is E2.
But isn't that redundant, because the edge set of G is already EG union EH?
So the edges in here are contain a point. Every edge in here is a point between an xi and an xj.
Oh, I see.
The edges in here are between a yi and a yj.
Okay, I get it.
Now I'm adding edges. These are definitely not edges that I've used at this point. So these are brand new edges. That's their only purpose is to increase the degree of this point and increase the degree. Is that clear? Okay, so I created a graph. Notice it's not a multi-graph. I've created a graph that has exactly the properties that we want. Okay? Questions? And although this may sound like painful detail, it's that detail that you should be getting in the habit of using, because the proofs are going to get a lot more complicated. Okay? Now, a lot of times when I'm proving something in class, I might skim over something, I might use a picture. If you want to see the details, be sure that you ask me for details. Okay? Questions? Questions about this? This isn't one of your homework problems, right? Homework problem was number 10. Oh, that gets really hard. Just thought I'd scare you. Okay? Any? So start where? Plus sign where? Right here? What do you mean plus sign? What does it mean to have one set plus another set? Oh, that's called the union. Right. Everybody, I'm just using notation. I think you all understand.
Yeah.
I hope. Right, this is the union. And at some point, I might use this symbol. You know what this symbol is, right? They're pretty, yeah. Sorry. Okay, if there are things that I use, please stop me and ask about it. Okay, questions? Oh, I can't wait to see those homeworks. Okay. Okay, so. Well, it's I'm erasing this if that's okay. And there's lots of problems that you can practice writing down in detail some of these proofs. I understand that a picture might help. But turning in a picture like this, if you just give me a picture like this, G and H, and go like that, I can't. That doesn't tell me anything. Deep down, I know what you mean, but you really want to write it down in detail, because the proofs are not going to be like this for forever. Okay. Okay. Okay, so I think we've talked about it. So I have a Legibia graph. Two vertices, x and y, are said to be independent. If and there's lots of ways to say it. If x and y is not an edge, or if x and y are not adjacent, which is the same as saying that it's not an edge. And one of the things that we're going to want to do, one of the important concepts when we study graphs in more detail, is looking for find independent sets. And the key is as large as possible. So clearly we can find independent sets of size 2 pretty easily. But if I ask you, what's the largest set of independent vertices? Now, what does it mean to be independent? You're going to give me a set of vertices so that no two are adjacent. What's the largest set of independent vertices you can give me in C5?
2.
There's no 3? Oh, 1, 2, yeah, so 2 is large. What about C6? 3. What about, and this, you probably realize that this is my favorite graph. What about Q3? Well, Q3, this is better known as the three-dimensional, oh, it looks like a, from over here, it looks like a cube. Okay, so you combine a set of 4 independent vertices. Oh, I forgot, here's a point. Okay, and it turns out that Q3, everybody, that's a set. Those are non-adjacent, those are 4 non-adjacent vertices. Now this graph has a very interesting property that the vertices remaining also form an independent set. So what we're going to want to do is take a graph and partition it into independent partition. What does partition mean? Just subsets? Partition is a very particular. It has all the elements. Just that's it. Just the whole set has all the elements. Okay, so if I want to partition this, let me say I want to partition Q3, the three-dimensional cube, into sets of independent vertices. Now, can you give me a partition of Q3 into 3 sets of independent vertices? Yeah, there's always a cheater in the room. Okay, so let's, I gotta call these, I gotta label these. Okay, so if I label this A, if I label this, let me label this, let's be grown up about it. 111, 110, 101, let's see, 011, let's see, I got 010, 1, 1, 0, 0, and 0, 0, 1, and 0, 0, 0. So let's label the points like that. Now we go back to our three-dimensional vectors. I'm putting 2 vectors, how many three-dimensional vectors with 0, 1 entries? Let's see, I got 2 for the first entry, times 2 to the second entry, times 2 for the third entry. So the total number of vectors, 0, 1 vectors of dimension 3. Say 8. 8, 2 cubed, right? There they are. And 2 are adjacent if they differ in exactly 1 component. So give me a set of, well, give me, if I ask for 2 sets of independent vertices that partition the vertex set, there is 1 such set. Okay. Now there may be others. Okay, there may be other such sets. Okay, so alpha of G is called the independence number of G, and it is the order of the largest independent set in G. Independence number. And finding the independence number in terms of applications and in terms of certain properties of the graph becomes pretty important. And there are lots of algorithms to do this. If you have studied any computer science, this is, in fact, it's very hard to find the size of the largest independent set in general. I give you any graph on 7 million vertices, I make up the edges, and how do you find the largest independent set in that graph is a difficult problem. It falls under what's called NP-complete. So there's no polynomial algorithm to actually do this. But this idea of independence becomes pretty important as we study the structure of graphs. A graph whose vertices can be partitioned. I'm using grown-up words, and you're going to ask me if you don't understand what that is. Partitioned into two, a graph whose vertices can be partitioned into two independent sets is called bipartite.
These pictures, the bipartial is like this.
So Q3 is a bipartite graph. Okay? Oh, wait a second.
Yes. No.
Yes or no? Those are the only two possible answers. You voting no?
Yeah.
Anybody voting yes? You vote yes?
No.
Oh.
I had a question.
Oh, you had a question. Okay.
So do the two subsets have to be the same amount? Like,
Nope,
like
nope.
that one, they were the same
No.
amount?
Okay. So let me give you one. Just to make it interesting. Here's a graph. Can you partition the vertices into two independent sets? Do you want me to label them, or can you just do it by saying point? Okay, so one more time. I want to partition the vertices into two independent sets. Which are they?
The one down on the right. These two.
Those two? Okay, so here's one set.
I mean the one down here and also the one I can draw.
You want to draw it? Okay. You're not going to add any edges, are you?
This two.
Oh, wait, whoa. Stay there. Are these two independent? No, what does it mean to be independent?
You want inside.
I want two sets of independent vertices. Okay, one more time. So as soon as you take this point and any of these, they're not independent. Well, does everybody see that this point is not independent from these points? Okay, so I'm going to ask again. I want two sets of vertices that are independent. Oh, okay. Wait a minute. So we could be here a while. Okay, there's a set. Okay, but it's a partition. So the problem with the other part. What are the vertices that are left?
Always you have two.
Yeah, but I want two sets of independent vertices.
Yeah, actually this side and this side.
Okay, so but we want to partition the vertices. We want all 8 vertices in two sets, so that the two sets are independent. It's not impossible. Someone help her.
No, just
To be congruent sets.
the one of the bar animals. Yeah, these two become a set, and all the others.
Okay, so in particular, if we take this as one set, they're independent,
Yes.
and this is the other set. So now we've partitioned the 8 vertices into 2 sets. Both of the sets, this set is independent and that set's independent. Okay? Good, thank you. Okay, so this idea of partitioning vertices into independent sets will become very important if you go on in applications. It becomes important as far as some of the applications of graphs and networks. But I want to get some terminology down. I don't think I've done this yet, right? A graph G is bipartite. So you have a graph G. Remember G, when I say a graph G, you're thinking, without me telling you, you're thinking vertices and edges. That comes with the terminology G. You're thinking vertices and edges. So a graph G is bipartite if the vertex set of G can be partitioned into by 2 sets. So the vertices are partitioned into 2 sets so that X and Y are independent sets in G. Is it clear? So let's see. So Q3 is a bipartite graph. C6, is C6 a bipartite graph? This is C6. C6 is a bipartite graph. Can you show me I have to partition the vertices into 2 sets of vertices that are independent. I'm going to pick a vertex. Okay. Okay, so I'm going to pick a vertex, skip one. Okay, so the blue are independent, and the non-blue, notice, are independent. What about C7? No. Okay, you can't do the same thing. C7, you can't, is not bipartite. What's an even number? What? Oh, see, okay. So don't get crazy. So what about hold on. What about this graph? So here's an odd number of vertices. What about that graph? Oh, what? Wait a second, what? It's like a theorem.
Oh, okay.
What is it? So C 2n plus 1, okay, for any integer n, any non-negative integer, any positive integer, you don't have a cycle of 1 point. So any positive integer n, Cn plus 1 is not bipartite. Okay, so now let's see. Not only is Cn, but if I have, not only C2n, but if I have a graph that contains a C2n. So imagine I have a K2n. So does adding more edges to a C2n, can that be bipartite? It can? You sure? So when I add more edges, let's say to C5, maybe 5 is too small. When I add more edges, can this be bipartite? No, because,
Because C5 is not part-time, so
bipartite.
yes, so even you add more,
Edges just gets worse. Whatever worse means. So if I have a non-bipartite graph, adding edges is not going to make it bipartite. It will only make it worse, whatever that might mean. Okay, less bipartite. No, it's not. There's no degree of partightness. What if I add more edges in? Okay, so can I add more edges into C6? Well, let's look. So if it's bipartite, then there is a bipartition. Bipartition. So if it's bipartite, then there is a bipartition into two pieces that are what? Independent. Very good. Okay, so I'm looking at C6. So I'm going to draw the 6 vertices, and let's see. So I'm now going to draw my C6. There's a C6. That's also a C6, right? Okay. Can I add more edges to that?
if you add more edges, it's the same. Still should be the right.
Okay, so how? Give me an edge that I can add. Let's call it A, B, C, and X, Y, Z. Is there an edge that I can add?
Yes, like connect A and B, B and C.
Oh, whoa. Careful. Okay, so here's a bipartite graph. This is C6.
Yes.
Okay, so now there are certainly edges that I can add. The partition of the vertices into two independent sets of A, B, C, and X, Y, Z. If I add this edge in, is A, B, C an independent set?
As long as you match between the two elements of the two different sets.
Okay, so I can add an edge from C to X. Notice, I still have the bipartition. I'm partitioning the vertices into two sets that are both independent. So in fact, I can add this edge, and I can add this edge, and can I add any more? No, at this point, every vertex in this set is adjacent to every vertex in this set. Okay. All right, so let's talk about this. So graph is bipartite if the vertex set can be partitioned into two independent sets. Is it black? Now there's a bright. Yeah, that's good. Okay, so we know what bipartite. Notice I underline the bi. I mean, it's like, the thing about graph theory is, whatever you think is the next definition, it probably is. A graph G is tripartite if the vertex set can be partitioned into V1 union V2 union V3. And I'm putting these dots here because it's a partition. Not only is the union of these three sets equal to the vertex set, they don't intersect at all. So a partition. You all know what that is. So if I can partition the vertex set into three sets where each is independent. It's tripartite. Yeah, but mathematicians never stop at 3. So we're going to define what it means to be k-partite. If you had to guess, a graph G is k-partite. If k-partite. What do you think? If V of G, if, that didn't last long. If V of G can be partitioned, right? And partition means there's no overlap, into how many sets? Into k sets, so that Vi is independent. Now, if I take any graph on n vertices, I can make each vertex a set of independent vertices. So any graph on n vertices is n-partite. It's not very interesting. We often want to find the smallest k so that G is k-partite. Okay, we want to find the smallest k. Okay? So let's go back to C5. C5 you told me is C5 bipartite? C5 is not bipartite. Is it tripartite? Can you partition it into 3? Partition the vertices into 3 pieces so that the 3 sets are all independent. I'll trust that you can do that. Okay, you can even have a single. Okay, so now it's going to be a matter of finding that smallest k, and we're going to look at problems where we're determining that k becomes important for what we're trying to establish. Okay, questions about this? So let me just let me put up a general. I'm looking at a bipartite graph. And this is, let's say this is V1, V2, V3, VK. K is not good, let's say VM. And this is W1, W2, up to Wn. So this graph has m plus n vertices. How many, so how can I count how many edges does this have? Can you give me a formula for the number of edges in this graph? Let me back up. Can you give me a formula for the number of edges in any graph?
The sum of the degrees.
The sum of the degrees is what?
Double.
Is double.
The number of edges.
So if I take the sum of the degrees, so the degree of V1, degree of V2, degree of V3, degree of Vn, plus the degree of W1, plus the degree of W2, plus the degree of Wn, and I add those up, we have twice the number of edges. But in bipartite graphs, we have a very special property. Now, do I need to sum up all of the degrees? So can you give me a formula for the number of edges in a bipartite graph? Number of edges is equal to the sum of the degrees of the VI's from I equals 1 to m. Well, what do I know that? Let's see, all the edges from here go down to here. So if I count the degree of V1, that just counts these edges. And the degree of V2 counts just these edges. The degree of Vm counts these edges. And each edge is counted exactly once. And this is equal to the sum from j equals 1 to n of the degree of Wj. So now we don't have to worry about double. I just need to count the degrees of one of the parts. Do what? N squared? What's n squared?
The n is the number of how many the edges.
So n is, I got the n vertices down here, and m vertices over here. For example, they don't have to be the same size, right? So here's a bipartite graph. Yeah, okay, that's an interesting bipartite graph. Degree of this is 3, 2, and 1. Sorry, 3, 2, and 2. So how many edges are there? 7. Does that make sense? 1 plus 2 plus 2 plus 1 plus 1? 1 plus 2 plus 2 plus 1 plus 1 is 7. Okay, so in fact, okay, so it has nothing to do with the number of vertices. Okay, questions? Okay. All right, so let's go back to on page 100. I think I want 100. Yes, page 100. Here are 1, 2, 3, 4. Here, 1, 2, 3, 4, 5, and I'm going to give you a 6th graph. 6th graph. Okay, so here are 5 graphs. But basically, it asks, are these bipartite graphs? Or which of these are bipartite graphs? Or something. It says, determine whether each of these are bipartite graphs. And I want to give you one more. That one. Okay, it almost looks like A, but it's got another C form in it. Okay?
我以为长条是绿的，其实浅，最开始有点绿。他问啥？问这些哪个是掰，哪个不是掰？说最后一个都是掰。Bipartite。我觉得这个课越来越往一个无法应用的方向走下去。我感觉我到时候做那种只会画图，真的。我感觉他这个是橄榄，所谓的橄榄算不把个西美日那种，西美不是巨秀的橄榄色脸盆，浅棕色。我真的很喜欢那小姑娘的长相。让我想起了方格子裙子，虽然不知道为什么，就是没有任何就是字面意思。方格子裙子，一种比栗色稍红的棕橙色。我觉得栗色应该。栗色我觉得就是栗子的颜色。哦，有可能。好想吃栗子。美国人这卖栗子，我觉得应该有，反正街边没有吧。他们栗子肯定。
Okay, so here are 6 graphs. You changed your answer. Okay, so let's start with, which one do you want to start with? Upper left? Upper left? What do you say?
Yes.
Yes. How do you know that? So we believe this is a yes. We believe this is a yes. So, by the way, how are you figuring out that it's a yes? What do you need to do? What do you mean just do it?
Just get two sets of independent.
There you go. Partition the vertices into two independent sets. Just do it. Okay? All right, so can you just partition the vertices in that first graph into two independent sets? Okay, everybody vote. It looks almost unanimous. What about this one? Yes. That's pretty easy. Someone tell me how to do that one. Top and bottom, and the middle. Okay, so just that sort of ices it. What about this one? I mean, it's almost, it just doesn't even matter what you. Oh wait. Oh, there we go. So there are 5 vertices that form an independent set, and here are the other 4 that form another independent set. Okay, so I left the last 2. What we decided about C5, right?
Yeah.
C5 is a no, and K3, and forget this edge. No. In fact, what's the largest independent set you can find in K3? 1. What's the largest independent set you can find in Kn? 1. So this is gonna take more than 2 sets to break it up into independent sets. So this, in fact, is tripartite. Okay. What about this one? It kind of looks like this one. So, okay, so then we vote. Anybody yes? Anybody have a partition of the vertices? I mean, there's only what, 8, 9 vertices. A partition into sets, into 2 independent sets. Anybody not have a partition into 2 independent sets? So can anybody prove that you can partition this into 2 independent sets? That you can't. Can you prove you can't? Can you prove that you can't?
Yeah.
Okay. Want to tell us?
The top vertice, the top of the house, has to be in one of the sets, right?
Okay.
A partition. So
Okay.
say it's in one of the sets.
Okay.
It's in the circle set.
In the circle set? Oh, in the circle. This circle.
Yeah.
Is that what you mean?
Yeah.
Okay.
The circle.
Okay.
All right. So then the 2 adjacent to it have to be in the X set.
Oh, good. Okay. So
Or the
they're in the
square set.
square set.
Yeah. So the 4 adjacent to those 2 have to be in the circle set.
So the 4. Oh, wait a second. I can't do that.
Yeah.
Okay. So there's a proof. Now another proof is, forget the bottom stuff. Look at this graph. Look at this. Look at this subgraph. Look at this subgraph on those 5 vertices. And it's not just like a C5. It is a C5. And what you tell me about C5? It's not. So, okay, so this is interesting. Okay, so if it contains a C5, that's bad. What if it contains a C3? Oh, that's pretty bad. Right. Okay, what about a C7? Let me see if I can draw a C7. Okay, what about C7? No, because it's odd. Okay. So I mean, we can actually do this, by let's color. Let's not coloring. We're boxing squares, squares and circles, square, circle, square, circle, and now you've got a problem. C9. Okay, so here's the key. So here's the amazing thing about bipartite graphs. Can't have any odd cycles. Okay, and that's a characterization. A graph G is bipartite if and only if, so it's a characterization, G contains no odd cycles. So I'm going to sketch a proof of that. Suppose G contains an odd cycle. So suppose G contains an odd cycle, and here's a we think that this is a bipartition. We think that this is a bipartition. So let's see. Let's say the odd cycle is x1, x2, x3, x2k plus 1. And they're adjacent. That would be an odd cycle. Okay, so without loss of generality, let's assume that x1 is in the top. If it's in the bottom, we'll just move it, we'll just swap it, right? So x1 is here. Where's x2? On the bottom. Where's x3? And it doesn't have to be next to it, it could be anywhere. x4. And we continue until I get down to x2k. Here's x2k minus 1. Okay, so let's look. I got this and this and this and this and this and this, and finally this. And now I need x2k plus 1. Now, what do we know about these two sets? What do we know about? This is bipartite. So what do we know about this set? It's independent. What about these sets? These ones? Okay, so now where can x2k plus 1 go? Okay, can x2k plus 1 go here?
No.
No, why not?
It's in the same.
It's in, that would put an edge there. Oh, so x2k plus 1 must be up here. Oh, but wait a second. The x2k plus 1 is adjacent to x1. Oh, that means. Okay, so there is a characterization of bipartite graphs. A graph G is bipartite if it contains no odd cycles. And in fact, even only if it contains no odd cycles. Okay, one more time. A graph G is bipartite if and only if X union Y is a partition. Well, so we don't even need this. If and only if G contains no odd cycles. Okay, so there's a lot of problems about bipartite graphs, and I want to get to the very next step. I want to look at number C, graph C on page 100. Graph C on page 100. What can you tell me about the cycles in graph C? Well, first of all, are there any odd cycles? No, because we said it was bipartite. Everybody is looking at the same graph C that I think I'm looking at. So, look, the characterization of bipartite graphs is that it contains no odd cycles. So graph C, does it contain any odd cycles? Let me make it even easier. Does it contain any cycles?
No.
No. So we have a very special class of bipartite graphs. And I'm going to change letter. Don't get upset. A graph T is a tree if it is connected. Connected, what does that mean? Connected? I always forget that. Every two, I close my eyes, I choose two vertices, there's a path connecting them. There's a path joining them. Okay, a graph T is a tree if it is connected and contains no cycles. Okay, so in this problem, here is a tree on 9 vertices. Here's a tree on 9 vertices. Take a minute and draw, don't look at the tree on 9 vertices. Draw your favorite tree on 10 vertices. Tree, and remember, a tree, it's connected and contains no cycles. Okay, does everybody have a tree on 10 vertices? Okay, now, don't shout out, don't shout it out. Count the number of edges in that tree. Okay, now I'm pretty sure that amongst the 20 of you that there are different trees, that you all didn't choose the same tree. But I'll bet that your tree has 9 edges. We're going to prove this probably next week. T is a tree. T is a tree if and only if T is connected and contains, sorry, T is a tree of order n. I need the number of points. Order n. So the size of the vertex set is n. T is connected and contains n minus 1 edges. Okay? T is a tree of order n if and only if. So this is an if and only if statement. If T is connected and contains n minus 1 edges. I don't believe that. Draw a tree on 7 vertices. How many edges does a tree on 7 vertices have? Most important thing is it's connected and has no cycles. Draw a tree on 7 vertices. What do you get? 6 edges. Okay, so now, on your tables, now draw all the trees on 7 vertices. All the different trees, right? Different trees on 7 vertices. I'll start. My favorite one, I'll draw my favorite 2. Here's my favorite one. Okay, by the way, this is bipartite. That's good. It's a complete bipartite. This is K1N. K16. It's a complete bipartite graph, and we're gonna talk about that notation in a second. This is one of my favorite ones. So 7 vertices. Here's my next favorite one. 7. So, graph theorists love names. So the top one is called a star. It's not called a star because you draw it like that. It's called a star because typically you might draw it like this. Oh, look, it looks like a star. And this is a path. Again, here are 2 trees on 7 vertices. Are there more? Wow, got quiet. You can talk amongst your table mates.
彻底是啥？我看我写没有 cycle， 不是 T S tree 什么 N over N 啊，对。然后 T is connected N certain image。它这个还有根本就很多呢，画不到尽头。挺多的，挺多的。
Do we think we got them all?
Yeah, actually, I think they all have by passing.
Oh, wait, what? What? Wait a second, they're all bipartite?
Yeah, I think if they
Okay, wait a second. What does it mean to be bipartite?
two independent step, the graph can be.
Oh, wait. What does this say?
So a graph is contain all cycles.
Okay, how many cycles does a tree have?
So nothing?
So does it have any odd cycles?
No.
Oh, so every tree is bipartite.
Yeah.
Okay, so now you're going to use the bipartiteness to, so here's the bipartition. I'm using words that hopefully make sense. Here's a bipartition 1 and 6. So now you need a bipartition 2 and 5. And it needs to be connected. How many edges? 6 edges. So I need to put 6 edges in here. Let me start like this. So, no. And then, how about that? Okay? Is there another one with a 2 and a 5? When I say 2, the parts, this is bipartite, the parts, 2 parts, or the partite sets, this is 2 and 5. Is there another one with a different one with 2 and 5? Careful. Yes or maybe. Those are 2 pretty good answers. How about this one? Are there more? Okay, so what I want you to do for Tuesday is come up with and don't Google it because you'll find it very simply. Draw all the trees with 7 and 8 vertices. Okay, one more time. The number of vertices is 7 or 8, and the number of edges is going to be 6 or 7, and the number of cycles in the graph is going to be 0. Okay, so that should keep you occupied for a while, and then we'll talk more about trees. It turns out that trees are pretty important when you come to applications. We're not going to do much with applications of graphs. Trees, spanning trees that are subgraphs of a big graph that contain all the vertices become important when we get to applications. Sorry, when you get to applications, we're probably not going to spend much time with applications. Okay? And of course, one more time, trees are bipartite because not only do they not contain any odd cycles, they don't contain any cycles. Okay? So have a good time, draw some trees, make sure they're different, and we'll see you Tuesday. Pam, you didn't tell me to turn this on.